Okay, so we should be going live right now. I'm going to get the stream pulled up on my phone here in a second. Once that's refreshes, there's a good 20-30 seconds of latency usually, so I'm gonna do that, check to make sure that that's all working, and then we'll get started here. I'm also have to share out links and stuff. Oh, there we go. So I want to go to current. Okay. Alright, looks good. Mute that. And I'm going to share links around. Post it to Facebook. Actually, post it to Facebook, Chief Delphi, Twitter. All of the usual places. Get this going here. Alright, that's Facebook, that's Twitter, and Chief Delphi. I'm not sure if I can edit this post now because I made it. Oh, I can. Actually, I'm not going to do that. It's going to be easier just to reply to it. There we go. Alright, all of the various and assorted places have been notified. Now, for some reason, my phone like freezes live videos when when I minimize it, but we should be good to go. I was getting sound on my phone and it was looking okay. I'm not dropping frames in OBS or anything, so we should be good to go. Alright, so we got a few people watching. Hello, everybody. Haven't done any CAD yet. Just getting the stream set up, so I think we'll go ahead and jump into it and get started. Alright, so when we left off last time, we had gotten all of these blocks for these pulleys and everything put in up at the top, and we were starting to work on the bearing shafts. What we were talking about right there at the end is we're trying to figure out where exactly the shaft is going to go across this way, and how we were going to make that work. And I realized that I think I had planned to only put one bearing on this side to avoid having to notch these. Being said, there's such a tiny little amount that would need to be notched away to clear that I don't know how worth it that is. So we're going to kind of postpone that decision. I'm not going to go through and modify these holes to match this one up here until we figure out the bearing situation up here. Just because if we end up having to shift this down, I want to wait to make all the changes to that, to this, all at once. So, okay, so what we're going to go ahead and do here is just put some holes in this, and then put a bolt through it and see if we need to move stuff around to make it clear. So from there to there, so that gap there is actually like this distance here is actually narrower than one of these bearings. So we might have to like step the bearing off to the side a little bit, which shouldn't be an issue. Alright. Okay, so what we're going to need is a hole in this flange that goes all the way through, and then a corresponding hole out at the end on this piece here. So let's go ahead and open this up and take a look. I haven't really touched this since the last live stream. I kind of intended to do a little bit of cleanup work, but didn't end up having time. I would have streamed earlier, but didn't end up having time this weekend to do that either. So let's just look at this here. Yeah, there's just, like, that's just not going to fit. I have this enhanced highlighting on, which allows me to look through. So if you use Inventor and when you hover over parts, it doesn't show up like this. It's an option called advanced highlighting that you can turn on. I highly recommend it because it allows you to do stuff like this where you select components and then you can look at them through other parts, which makes it really easy to do stuff like what we're doing now. So basically, the bearing itself does not need to fit here because the bearings will be presumably off to either side of this pulley. However, the actual bolt itself does, and whatever spacers that we put on the bolt, which are probably going to be about 3/8 of an inch. So we need quite a bit of room. And there's also going to be spacers on these pieces here. So we have basically a couple of options, and what we're probably going to have to do is end up using a combination. We can move these up to get a little bit more space underneath, and we can also move this stuff down to make room for a shaft with the bearings to sneak across here. I think we're going to have to do kind of a combination of both just because of how crunched for space we are. Like I said last time, this is mostly just an issue on this top stage. It's not really an issue on the other stages just because everything's spread out more width-wise. However, it's kind of still an issue. Also down here, I don't know that we're going to be able to use a bolt for that. Well, we might be able to find a 5-inch bolt. It's pretty long. Alright, we'll cross that bridge when we come to it. I'm going to throw a nut on this side real quick just to make sure... Oops, I didn't want to open. Place. Just to make sure that it clears everything. Do we not have a... We don't. Do we have one from something else? I don't think we do. I'm just going to go ahead and go to Mcmaster-Carr and download a new one. Alright. I want 1/4-20. Lock nut, zinc plated. I think it's pretty sure we usually get just the low strength ones. Actually, I can look because whatever we usually buy, I want to just make sure the part number matches what we usually buy. It's not particularly important, but because I'm throwing this in Stellar's 011, wait, what? These are different parts. I don't, yeah, you know what? Never mind. It doesn't matter. Okay. I'm just going to do the grade 5 because that's probably what I would actually buy, just because it's like 10 cents more for a pack of 100. Plus I would buy these from Bolt Depot anyways. Alright. Okay, so nut, nylock, 0.25. Can't do like ZP for zinc plated. Delete out that stuff, leave the part number. Yeah. Normally I would order these from Bolt Depot, but I always download the models from Mcmaster-Carr because Mcmaster-Carr has all the correct models, whereas Bolt Depot doesn't have CAD as far as I know. Alright, nut, where is it? It's down here. Oh, my computer froze up there for a second. Nut, nylock, there we go. Oh yeah, so I do, for quarter 20, I do 0.25-20 because you can't have a slash in a file name, so you can't do the actual fraction. So that's the reason why I do that. It's not a typical way of noting a thread size, but that's why I do that. Computer's being a little bit laggy. I hope that's not corresponding to any stream lag. Alright, and then I'm going to turn on and the only reason that I'm really taking the time to do this is because the nut is bigger than the screw, and I just want to make sure it actually does clear all of this stuff from the from a top view. So we'll check that out here shortly. Oh, that's not actually long enough. Okay. Well, there's a solution to that. These. Thin lock nuts. They're not really any more expensive. They're actually cheaper, obviously because they're smaller. Used these for a few things before, not quarter 20, but alright, we'll see how one of these fits. Cut that out of there. Oh. I should just leave standard parts up. Alright, nut, nylock, low profile, zinc plated. Honestly, this is the most time-consuming part of doing design, is just going and getting all of the off-the-shelf parts that you need. On Stellar Robotics, we typically don't put in all of our fasteners and stuff. Actually, we hardly put in any in our CAD models just because of how time-consuming it is. But for stuff like this, especially since I've never designed a telescoping arm before, I want to make sure that I account for all the various clearances and things that we need to worry about. Alright, so now we'll insert those in there, and we'll make sure that the nylock sticks out far enough that the screw threads can catch it. Because them being nylock nuts does you no good if you can't engage the nylock. Alright, so that's perfect. That's what we need. And actually, in reality, I don't think I clicked the right thing. In reality, you wouldn't even tighten these bolts down. You would just get these to the point where they just barely touch this sheet metal. Because if you started to tighten it all, you would just bend this flange inwards. The screw just acts as a shaft. There's absolutely no other purpose to it than that. And we're good for clearances, so all this stuff clears. You know, as it slides up and down, it doesn't hit this. So, all right, perfect. That's what I wanted to check. Let's move. Actually, no. Let's just get these holes in here real quick. Absolute minimum. That is 0.25. So absolute minimum, we're going to need 3/8 of an inch between these vertically so that the spacers can pass by each other. I suppose we could go a little bit smaller than 3/8 of an inch diameter for the spacers, but we're gonna go ahead and plan on that and see if we can make that fit for now. All right, and then I'm gonna put a construction circle in here. That represents the spacer. That represents the bearing. Oh, and I should put one in here. That represents the hole. Okay, and then actually. I forget. Right, 5/8. Alright, so from there, I'm doing this in the right spot, correct? Correct. Okay, so need, no, not that. Line across the top, and a tangent to this bearing here, and then dimension this like so. Alright, so then this top dimension is going to be 0.25 plus 0.375. And then we will put our hole. Must have had the settings in there from last time. Alright, so we're going to put that in there. We'll see how much interference we're dealing with. Probably a lot. Alright, so then for that same part, actually, we need to basically... Oops. We need to basically mirror it. Actually, I think we can mirror it. How did I model this? Did I do it in an intelligent way that makes that easy? I think I did. That plane, 1.125. Yes, I did. Okay, cool. So, can mirror this feature by that plane, and that works out perfectly. So now these holes line up, because you got to get, because this part and this part are actually the same, and they're just rotated by 180 degrees. If you didn't watch the stream last time, obviously you can go back and watch the archive video, but these parts are supposed to be common. That's not actually really necessary, because like we've got this notch over here that's not needed at all, because the pulleys are staggered, one on this side, then this side, then that side. So depending on how different the two parts would be, like if we end up adding a whole bunch of features that are only needed for this belt run that goes down to the bottom, and we feel like it would be cleaner and stronger to have a solid piece without all these cutouts in it on the other side, then we'll just split the parts off, do a save as, delete out the stuff we don't need, and do a replace on this part. But we're a long ways away from needing to worry about that right now. So, okay, so these are the 2.5-inch bolts. So we're going to grab a couple of those. 1/4, 20, 2.25. Wait, what? There we go. Wait, why is this? Oh, these are 1032s. Okay. Alright, and we'll put them both in from this side. The side that the head is on, the side that the nut is on, is not particularly critical, because you don't have to worry about the nut hitting this, but the head not hitting it. Alright, so getting these guys in there. And I think probably, oops, did I hit escape before I think I did. Enter, there we go. Okay, so we have full-blown interference here. And in order to get rid of this interference, we've got 1/8 of an inch of interference there, so we'd have to raise this up by a full 1/4 of an inch. Or we have to raise this by a 1/4 of an inch, or this down by a 1/4 of an inch. So the question that we've got to ask ourselves is, we have 3 options, and we can do any combination of these 3 things. So option number 1, plan on making the spacers a smaller diameter for this. I'm planning on 3D printing them, which is why I stuck with that 3/8 of an inch diameter. However, the inner race is only call it 0.35, so we could shave off 25 thousandths easily. Going any smaller than that is just going to be hard to print, but we probably could get away with it. That's not my favorite option, though. Alternatively, one of our other options is we can move this whole guy down, And then the other option is we can move these up. And the only problem with that is just how close this hole gets to the edge. So right now, we're not that close. Minimum distance is a little over 1/8 of an inch. I think we can do a decent amount more than that. So we're going to do a combination of all three, I think. I think we're going to go to 0.35 on the spacers. I think we're going to move this up a little bit, and I think we're going to move this down a little bit. And between all three of those, we need to get 1/4 of an inch. So I think what we're going to do is start here. Get those. So we'll go, we can go let's see, so if we do 0.07, so if we get, that's like absolutely as far as I want to go. I don't want to go any farther than that, because that leaves us with like 73 thousandths. Yeah, 73 thousandths, which is not bad. It shouldn't be a problem. If you weren't in on the stream last time, we talked about the issues here, but these parts would be laser cut, and basically the laser heats the metal when it cuts. Obviously that's how it works. So the laser melts it, and then there's a gas jet that basically blows the molten metal out of the cut. But you know, some of the metal around the cut is heated too. It's by conduction, especially in aluminum. So aluminum is especially bad because it is very good at conducting heat. So when you make a small cut, a large portion of the sheet of aluminum gets hot just because the aluminum is so good at conducting the heat away from the cutting area. And so basically, so the whole area around the cut gets very hot very quickly. And then in addition to that, aluminum also has a very low melting point. And so what happens is you get, if the laser's like cutting around this hole and you get to this thin part, basically heat is trying to spread out from the cutting area, and it kind of gets trapped, right? It can only escape out this way and this way because presumably you've got a cut in it, so it can't jump that gap very easily. And so it can't really escape anywhere inside, and so it can't escape this way because it would have to go across an open gap. And so basically the heat has a limited route of escape, and so the heat tends to build up in the thin areas when you cut beside them. And so basically it's pretty easy to have a very thin area exceed the melting point of the aluminum, and then it basically just melts all the way through, and you end up with a hole here. This is not really particularly close to that limit. Like, this would not melt through. I couldn't exactly say what that limit would be. I would say it's probably closer to 30 thousandths, or maybe 40. But I'm not really comfortable going any thinner than about 1/16 of an inch, which a good rule of thumb there is don't go any closer to the edge than one material thickness. But if you really want to push it, you can get away with less than that if you have to, but I don't know how much you can get away with. So I don't know if that explanation makes sense, but that's kind of an important design consideration when you're dealing with laser cut aluminum. So yeah. All right, so now let's actually, real quick, let me grab this dimension number that we had. So that's D82. So I'm going to just replace over here this dimension here. This here should just be D82, so we don't have to keep going and updating it. And then that's going to become 0.35 because that's the diameter of the spacer, so that moves that up quite a bit. Alright, so that should have gotten us 0.05. That should have gotten us 75 thousandths. So we need to move this down the remaining amount, so 0.175. Let's give this an update real quick. So yeah, still a good amount of interference. And actually, I hadn't considered something. I hadn't considered the fact that I hadn't considered the fact that the spacer would interfere too. All right, we might need to take a little bit of a different approach here. All right, so we have another option, and I was hoping to avoid it, but all right. So really quickly to understand how this solution will, how we can actually use this solution for these lower stages. I think what we're going to do is we're going to put these up at the top. So the ones that go this way, we're going to put those up at the top, and then we're going to put these down low. And the reason we can get away with that is because these blocks are in here and the bolts are way out here. So we can put the bolts as low down as we want. So we just don't have as much of an interference issue down here, especially since this needs to get moved down to match this too. And that's like I was saying earlier, this is correct. This and this are not in the correct position yet because we need to go and update it, but I'm going to wait until we finish this. So here, we can't move these down because they'll interfere with this, but on the lower stages where the stages are wider, that's not an issue. So what I think we can do is I think we can just extend this up a bit. We can just basically just make this stage a little longer. And I don't even necessarily think yeah, I'm not sure. I don't know how much to go. Probably a good amount. Probably half an inch. So that'd be up here. All right, well, let's just do it. Stop talking about it. Let's just do it. And then at the same time, we've got to lower this feature down more. So I'm going to just make the whole part. I'm going to add that in case we need to tweak it later. I'm not just going to type in 36.5. I'm going to actually do the addition. All right, and then I'm going to make this. Oof, I hate it. All right. All right, then let's kind of put this back the way it was before. Then let's kind of undo those tweaks that we did, because if we're going to go to the trouble of extending this whole thing vertically, we might as well give ourselves the safety margin that we had before. We'll look at what that looks like. What the heck is going on here? All right. And then let's just put this back to 375, and because we typed in this dimension earlier, we don't have to tweak that. It automatically adjusts. So if we look at the distance between these two, and we look at the delta x, it's 3/8 of an inch, which is what we want. All right, so that. And then what we need to do is update our constraints. That may have been too much. All right. Well, I'm not going to worry about it right yet. Just get this one. Nope, that was the first one. Edit the flush constraint. So this should be 2 now. Actually, we'll do plus 0.5. Wait, what's this constraint to? Oh, and then this one should reduce, because we don't, if we can, we don't want to get to the point where we're increasing the total height of the mechanism by doing this. So we want to end up like that. Unfortunately, that kind of results in not having a lot of mounting ability here, but we talked about making this longer anyways. So we're going to kind of keep it the way it is for now, and then adjust it later. We might shave another 1/8 of an inch off of this, but I kind of don't want to deal with that at the moment, so we're going to leave it the way it is. All right, so let's see here. Two bearings. So we can put these bearings basically wherever we want now, because I think there's enough room between this and this that we don't have to worry about pushing them off to the side so they don't hit this flange. So let's go ahead and put those in there. And get them constrained. Oh, come on. Okay. And one over there. Alright, so now I'm just going to do a flush constraint to all these sides, just like we did on the other direction. Alright, and then, yeah, there's no interference here, not even close. Let's look at actually what this gap here is, because that'll give us an idea how much space off the top we could take if we wanted to. Minimum distance is 0.130, and that's at a slight angle, so coming straight down is not necessarily going to cause the same issue. So we can come down 0.125, and there will be greater than a 5,000th gap there. Okay. This is a very, very tight, very, very tight space here. All right, let's go back, and I'm going to go ahead and take that 1/8 of an inch out now, just because I want it gone. All right, so this is why I did this plus, so that we can just go in here and tweak that value by itself rather than having to edit the whole thing. So now we can just go in and do stuff like that. That's just personal choice, no particularly critical reason to do that. I just find it more intuitive when I'm in the constraint box, editing constraints. Then we can do the same thing here. Just change all those 0.5s to 0.375s. If you're not familiar with all of the decimal equivalents to fractions, it's pretty easy to do. You know, on a calculator, you can obviously figure it out. So like 3/8 is 3 divided by 8, and it'll just tell you what the decimal equivalent is. There are also charts. You can find them if you search for a fraction decimal conversion chart. There's ones you can download and print off and put by your computer. When I first started doing CAD professionally as an intern, I had to do a lot of fractional to decimal conversions, and so I had a chart by my desk, and it didn't take me more than about a month of working part-time to have them all memorized. So that's a very good thing to have memorized, just so that you know what all the conversions are, or you know what, you just have the equivalents memorized. Alright, so that's fairly good. I think I'm happy with that. So I think what we need to do now, let's refer to our thing here. So this belt needs to mount down here. Oh, right, and we needed that shaft to go between the belt and the other stage. The bearings are 1/2 inch diameter. The bolt is 1/4 inch, so that leaves a, let me show here. So that means that this gap between the bolt here and here is 1/8 of an inch. because this is a 1/2 inch, this is a 1/4 inch, so half minus a quarter is a quarter divided by 2 sides, 1/8 inch on either side. So that means that there is, in theory, enough room for a belt to pass through here, but I actually think it doesn't actually fit because the belt teeth stick out. I'm going to do a little search here for HTD timing belt dimensions and see if I can find dimensions for the profile. I'm just going to go to images, see if I can follow the links through. I always have trouble finding these dimensions because I don't have them memorized. Okay, so overall height is 3.8 millimeters. And this is an HTD, 5M, which is what we've got. All right, so 3.8 millimeters is 0.149. So the belt is bigger than the gap that we have here. So that is a problem because down here, this bearing needs to roll on this surface and the belt needs to go behind it. However, what I'm not 100% sure of, because they don't actually need to move in relation to each other. So if we were okay doing something sketchy, we could trim the teeth down because this belt here is going to be bolted to this 1x1 tube. So the belt that runs on this pulley here is going to be bolted to this tube. And because this is a cascade rigging for this whole thing. So we could, if we were feeling lazy, just cut the teeth or even just squish the teeth. There's a small enough amount of interference, only about 25 thousandths of an inch, that it might not be an issue at all. Like the rubber of the belt might just squish, or if you're able to get the teeth of the belt to basically straddle the bolt, there might be enough clearance there. Which is okay, I guess. I'm just worried about assembly, like the ability for us to assemble this in a real life situation. So the other option is to get a slightly larger bearing that spaces the bolt away from the tube more. Oh wait, we can't actually do that because this doesn't roll on the tube, it rolls on the outer piece. Oh, wait a minute. So maybe this is not an issue at all then. So hang on. I'm an idiot. So those the bearings that are down at the bottom of this actually roll here. So there's an additional 1/16 of an inch. Yeah, okay. So never mind. That whole discussion was completely irrelevant. Yeah, so you guys are getting this live, folks, because, when I did the videos for the CAD class or when I, do other prepared CAD stuff, you see the end product, or if you see me modeling it, you're typically seeing me model it for the second time. I've typically gone through and modeled it once already to make sure that I know what I'm doing and I know what I want to talk about. But I figured for this, I didn't really want to model this and then remodel it to record videos of it, and B, I think it's fairly valuable to be able to actually see the live design process as it unfolds, because some of these mistakes and talking about some of these trade-offs and some of the different options we have is basically the hard part of doing design. It's easy enough to sit down, follow some instructions, and CAD even a very complicated mechanism. That's still pretty easy. But to actually work through all of the different trade-offs and the clearances and moving moving parts around to clear other parts, that's a pretty important thing to be able to do. So basically what needs to happen now is we need to design the brackets down here that are going to hold these bearings, and then we can put in the other pulley down at the bottom, which is going to be done basically exactly like it was up here at the top. We're just going to have to duplicate all these holes and slots and stuff down at the bottom. But we're going to have to pick out an appropriately sized belt before we do that. And also I just realized we need to have a way to attach this belt here. So these holes being here might be kind of a problem, because ideally we want to clamp it against the aluminum, but there's no aluminum here because there's a giant hole. So we might actually have to split off the pulley side and the non-pulley side earlier than I had hoped. But we're not going to worry about that right now. So we'll have to figure out a pulley center to center distance sometime soon. I guess the other question is why are these up farther? Is there any reason for that? Because I realized I could have made this full length. It doesn't do you any good, but it also doesn't hurt anything, and it ends up meaning that the upper stages have more support in the extended. Because right now we have the same overlap, which is this like overlap between these two. We have the same overlap for every stage. But if we wanted to make, like, for instance, this tube extend all the way flush to here, then you get an extra, like, 5 inches of overlap there. You're probably wondering, if you're not super familiar with how cascading elevators working, you might wonder why that wouldn't allow the elevator to extend up higher. And that's basically because every stage with a cascading elevator, short of some very complicated and creative rigging, which there was just simply not space for here. Short of doing that, each stage can only move in relation to the previous stage by the same amount. So like each one of these stages can only extend, for instance, 20 inches. Or in this case, it's like 32 or something. I actually don't remember. So from here, it's been a week, guys. It's I've forgotten everything. So 1.5, I don't even remember what it was. And then it was like 30, wasn't it? 31 or something. So 28.5 inches of extension per stage. Yeah. So each extension for each stage, not the amount that sticks out, but the actual extension. Well, I guess it's the amount that sticks out too, kind of, but it has to be the same for a cascading elevator. Anyways, that was kind of a rabbit hole. This has no real bearing on what we're doing right now. So basically we've got to get bearings that go, we have to crisscross the bearings like this again. So we've got to have like 2 sets of brackets, one that mount one way and then one that mounts the other, which kind of confuses the issue a little bit here. Yeah. How thick do we want to go? I don't really want to do 1/8 inch, but 1/16. Am I comfortable with 1/16? Yeah, we're going to do 1/16. Okay, so do this. So, oh right, what was the spacing? That was the question that we needed to answer. So from here to, oh right, what were they going to roll on? I think there were just going to be a single bearing here in order to miss this flange. So there's going to be 1 bearing here all the way down at the bottom, and then there were going to be 2 on this side. That doesn't affect our That doesn't affect our brackets though. So we'll do, okay, so, dang it, that was what I wanted to measure. So it'll roll on that surface and that surface, which is 2 1/8. So it'll be 2.125 minus 0.5, because half the bearing radius, but doubled on both sides. So those are the center points of where the bearings are going to roll. And I'm actually just going to go ahead and model the holes into this sketch rather than doing the holes later. And then I want a decent amount of meat here. So I'm actually going to do, I'm going to do it this way. Like that. So I'm going to make this, actually, I don't want to dimension it that way. I want to dimension it that way just for cleanliness. Where's the center point for this? Oops. Okay, center that, and then that's the center to center distance. We'll go that minus something like that. So that gives a little bit of clearance so that the bearings aren't exactly flush with the bracket, because the bearing will be this dotted line, so the bracket falls a little bit short. So this and this are not coaxial. The center point of this arc is here, and the center point of the circle is obviously there. So that's kind of some weird geometry, but it helps clean this up a little bit. Okay, so then what we're going to do is this. This is where we'll do most of our riveting. So that'll be 1 inch wide, so this will just sit flush with the edge of the tube. And then we can do that maybe, and then do 4 rivets. Or we can do that and do, just do 1, 2, just do, wait, 1, yeah, 1, 2, 3. We'll start with that. Okay. Like that. And we'll make these 16th and aluminum 5052 H38. All right, now the laser is going to leave a small radius in here, and normally I wouldn't care about it. But in this case, we're going to go ahead and model a relief to make sure it's actually a sharp corner, because there's basically going to be a bracket like this, and there's going to be another one that's basically turned 90 degrees and laying right on top of this. In addition, this is a fairly sharp corner, even if the laser does leave a little radius, so if there's any load on this that we don't like, it's going to tend to start a tear here. So turning this into like a big rounded undercut shape is actually stronger than a sharp corner. So we're going to go ahead and put that in here. So we're going to project. It's been a while since I've done this. I think I'm going to do it the cheaty way. No, I'm not going to do it the cheaty way. I'm going to do it the actual way. Right. Like I said, it's been a minute since I've modeled this. Okay, so then these dimensions, so they're 1/8 inch radiuses. And then I need a way to, no, that's not a good way to do it. Okay, so then I can use a symmetrical constraint, which I pick the 2 sides, and then the thing, oh, it doesn't like that. That's unfortunate. Oh, wait a minute. Yeah, I can't do that with that constraint. I guess what I'll do then is I'll just do this. I could just dimension it to a 45, but that feels wrong. I feel like I should do it parametrically. Also, that constraint got screwed up because it flipped sides on me. So now we just got to do a bunch of splits so that this actually can be extruded. Just turn that to construction. And then basically I just need to split that. And this line being in here, or this line being in here is not an issue. Actually, maybe it is. It doesn't matter. And then I'll see if I can mirror this to the other side. All right, so the other thing that this relief allows you to do is allows you to cut the shape on a router too. So this is, if you're trying to, if you have like a CNC router for your team, this is the way that you would model sharp corners, that you would relieve sharp corners for your router. So this could be machined. This shape can be machined with a 1/4 inch router bit. That's really big, so maybe we'll go in and set this to 0.125, and I'm actually just going to set these to be the same. So now this could be machined with an 1/8 inch router bit. So that's a useful trick. This type of relief is much more useful for routers, but I'm just using it in this case to prevent the creation of a stress riser for the laser cutting. So let's do a mirror plane. Mirror that to the other side. Then let's put our holes in. 1/2 inch there. 1/4 inch there. 0.196 for a rivet. Oops. Pattern the hole feature. Down. Put 3 of them. Should be plenty strong enough. And then fillet. Nice big fillets here. Alright. That's okay. That's not bad. And I'm going to go ahead and color this part because it's done. I don't have any more features to add to this part. I might resize it if I need to, but I don't think I'm going to need to. So I'm going to just go ahead and color it so that I know it's basically done. How to do this? Does it matter which is the bottom and which is the top? That's the other question. I think we want the so the belt's going to be here. So there's going to be a single bearing on this side and double bearing on this side. And as long as the bearings can clear, like there's enough space in between these bearings for the belt, just not the pulley. So there is 15.875 millimeters here. So there's 0.875 millimeters of clearance, so basically almost a 1/2 millimeter on either side clearance for the belt to go through here. There's just not enough room for the pulley because the pulley's wider than the belt for relatively obvious reasons. So single bearing on the bottom. Don't want to see all that. So single bearing here, double bearing on this side, pulleys over here. So we want the bearing shafts that go this way to be on the top. Okay, so let's see what we can do here. So, okay, so this will go like that. Those first, then we'll do the ones that go the other direction. I gotta kind of attack this at a weird angle just because I can't get to the parts, and I would turn off visibility, but I don't want to turn off visibility on everything, and I can see where I need to work. It's just a little bit unwieldy. Alright, so we're just going to flush these to the bottom. I may actually have to... Yeah, you know what? We're just going to do it. This will make our lives a lot easier if we just do it that way. Alright, so now what we're going to do is that guy and that guy will go those directions. And then we're going to constrain these above like that. So if my explanations before were not making sense, and I'm guessing they weren't because I was picturing all of this in my head while I was talking, which is never a very good recipe for me being clear. If that didn't make sense before what I was talking about, then hopefully once I get this constrained, it'll make a little more sense. Like that, and like that. Okay, so basically this relief here provided space so there wasn't a small radius left by the laser, which would interfere with this corner. You could relieve this more if you want, but this just barely touching that is enough. So then basically there's going to be a single bearing on this side and then two bearings on these sides. So like here, single bearing, over on the opposite side, single bearing, and then on this side between these two plates, two bearings, and on the opposite side, a single bearing. Now the question that we kind of have to ask, oh, and I kind of didn't think about this plate being in here. Oh, that shouldn't be an issue. Oh, it is. I guess this doesn't actually need to be full width. Like, we could cut it, which kind of defeats the whole purpose of this relief. It also makes it harder to assemble because you can't just push the bracket. It's really nice having the brackets flush with the edge of the tube because it makes them easier. You'd like make sure they're flush and then clamp them down and match drill the holes. If you don't have like a mill where you can set up on this tube and machine those holes directly, which my team doesn't really have access to a mill. We kind of do, but not for a large quantity of parts. So when we do stuff like this, we would just clamp this up and match drill it and hope it's close enough, which for most things it is, but linear motion is a fairly demanding application in terms of tolerances. We could cut some just small notches in this to clear bearings, which is going to make this part look really ugly, but that's probably the best thing to do, and it probably makes the most sense to delete these reliefs out and then just cut back. Alright, well, that kind of ruins the look of our nice clean part, but it's fine. So we're going to just go up, delete those out. Actually, I'm not going to delete them just yet. I'm going to delete this one, and I'm going to suppress that one in case we need to turn it back on. So what we're going to do here is project those and do... There we go. I'm sorry, I'm clicking on all kinds of random stuff. I just keep clicking on the wrong thing. So let's do a 0.25 because the bearings are 0.196, so we need some clearance. And then this should be like that. Let's do, yeah. Alright, so then we'll extrude those through all. And then let's add some small fillets here just to distribute the load. And the bearing just needs the clearance really in this area. It doesn't really need the clearance up this high or down this low. It's actually, let's change this a little bit. This does not need to be, it needs to be more like that. So how high is this? So this is right where the center of the bearing is. So actually we should probably not go down that low. We should go like up another 1/16 of an inch. And I'm doing all these like conversions and stuff. So like I just know what the next 16th inch increment is, but if you needed to do that math with a calculator, you know, you could do that too. So okay, well that's not as nice looking, but it accomplishes the same task. And then we don't need this relief here, obviously, because there's no corner. It's just a flat surface. So that is, so when you're, yeah, it's not amazing, but it's the best we've got right now. All right, so now we need to put a bolt through here. We could do a 1.5. We can't do a 1 1/4 because the plates eat up too much of the length. We could do a 1.5. I think that will fit between here. The problem that we've got to worry about, which I didn't really think about this before, but the problem we have to worry about here is, oh, this hits here. Oh, and that's going to interfere with every single rivet. That's not going to be good, because the rivets come through these holes and then they stick out, and they also expand horizontally too. I've always used a rule of thumb of, for 3/16 inch rivets, allow for a 1/4 inch diameter on the back side as well as a 1/4 inch tall. So think about there being a 1/4 inch diameter, 1/4 inch tall cylinder constrained to the back side of each of these holes. And that's the clearance you should give a rivet. All right, that's frustrating. We may have to do something a little different down here then, because I can't just trim this back a little bit to clear, because we've also got all the rivets to worry about. So we may have to do some sort of a 3D printed part or something. And because it's a problem here, it's also going to be a problem over here, because this flange is repeated when you have the other rotated part up here. So I know this is a little bit more boring than the last stream was, just because I'm trying to figure out how to do some of this stuff. But I mean, this is the critical part of the design process, so you guys get to work through this with me. If you're watching the video after the fact, you can of course skip ahead in the video and try to figure out what we end up figuring out. But you know, because I'm sitting here doing this, I don't have the luxury of doing that live. I can't just fast forward in my own design, obviously. That'd be nice, but that's not how that works. So, okay, so really what we need is basically, we've got a few options. So one way we could solve this problem in kind of a sketchy way is to like space the plates off a bunch. So we can't move them in any farther because the tube is here, but we could move them out to like way out here. That doesn't really help us get a bolt through there, but we could use a pin instead. We wouldn't necessarily have to use a bolt. Alternatively, we can come up with, oh, come on, some sort of a bent bracket where it's a little narrower and it's like a U shape, and the U shape rivets onto the tube. That being said, this is already only an inch wide, and I would hesitate to bend anything with a narrower U than an inch. So maybe that's not such a good idea. Another option is to 3D print a part that just does this job better than the flat plates. I don't really like that because that's putting a lot, I mean, it's putting like the bulk of the force in your mechanism entrusted to a 3D printed part. But for Stellar Robotics, that wouldn't be the first time. So that's probably what we're going to end up doing here. Yeah. So basically I'm thinking, instead of having two little prongs on either side, we've got one in the middle, and then we put a bolt through, and then there's a bearing on either side. It's not as secure of a mounting mechanism, but it is passable. And then hopefully with the screw head, the bearing, the 3D printed part, the other bearing, and then the nut, all of that ends up staying basically pretty close to inside of the size of this tube. So like an inch, or maybe, yeah, basically just an inch. That's basically all we've got, because stick out any farther and you're starting to get into the territory of these rivets. Alright, that's frustrating. So what does that part need to look like then? Thinking out loud here a little bit. So it would be nice if, so we've got to have something to come out so for the bolt to go through, and then it needs to have some way of mounting to the tube. It would be nice if it could come out to the tube and wrap around a little bit with some little like locating tabs to make it easier to like put on the tube and either bolt or rivet in place. That would be really nice. The problem is you can't have them on two sides and have part of it wrap around the edge. I suppose we could bring it to the edge and do like a 45-degree miter so that each of the four sides is identical, but it basically, yeah, so but it basically just acts like the one next to it is its own locating tab. Does that make sense? I don't know if that makes sense. Reading the chat here. Move the rivets. Yeah, that's, I suppose I didn't even think about trying that. The problem is we start running into issues with how close to this bend we get. But I don't know how much we need. So this is a 1/2 inch, I believe. We can definitely do 3/8. Maybe that's enough, because that's more than a 1/2 inch. But the real problem is this direction then. I suppose we could use a button head screw. Yeah, I suppose we could use a button head screw, and I can just shorten this a little bit. There's no reason this needs to be a full, like we can cut this off. We start running into that like melt through issue here, but I don't know that we have much of a choice. Minimum distance 60 thousandths. Oof. Okay. That's really tight. Oh, I suppose we could also just make this flange shorter too. Because if we move all these holes in, there's no reason we couldn't just shorten the flange a little bit. How much do we need? Actually, it's quite a bit. Oof. 3/16, and it's already. Alright, well let's just make that change real quick and see what that looks like. That might be the way to go. When you're trying to design something that's this compact, there's not really any good options. Okay, and then the other thing, I wanted to do the other hole. That hole and that hole. Make that 3/8 of an inch as well. Okay, and this needs to be shortened by probably a minimum of, that gets really close. Yeah, that's too close. That'll melt through for sure, or come really close to it. If we absolutely had to, we could put a little bit of a like like a, I'm not sure, like a extension on the side, because up here we don't have to worry about those brackets hitting, because those brackets only roll up to like somewhere around here. So this might not be an issue. We just need to add that material back in. These are far enough away from the edge, I think. Yeah, 77,000. So it's a little close. There's not a lot of meat there to hold on to, but they're not really that bad. All right, let's take a look at this. What this looks like in the assembly. As I've said a million times at this point, I've never designed a mechanism like this before, so I'm learning how to do this at the same time you guys are. Also, making these out of sheet metal is not a very particularly common thing. So a lot of this stuff goes in just a tube, and then they machine these holes in. So you don't have some of these issues with like the flanges interfering and the rivets sticking through. But I wanted to design this using manufacturing resources that Stellar has available to us, just because we're not heavy on the machining. We've got sponsors that do laser cutting for us. We can do, laser cutting ourselves. Some places we have some sponsors that let us just come in and do the laser cutting ourselves if we want to. But either way, laser cutting is our highest precision manufacturing method, and then 3D printing, and then obviously we have the ability to bend stuff pretty precisely using CNC press brakes. But yeah, it's kind of a weird way of building stuff. A lot of teams do have access to mills. Most teams that have access to a laser cutter also have access to a mill, but we're kind of a weird exception where we don't. So that's kind of why this is designed the way it is. Let me put it this way. I don't like it, but I don't see anything particularly wrong with doing it this way. Let's slide this up and just make sure it doesn't get... Yeah, and so this is where it stops, so there's no reason we can't just add a good old sized extension to that to make that back to where it needs to be. Alright, well I guess that's what we're doing then. Good suggestion, thank you for that. Trade-offs. I mean, this is what you have to do when you're designing stuff. Like, you can't get something for free. You're going to have to make trade-offs. You're going to have to sacrifice in some areas to get space or weight or performance in other areas. Alright, I'm going to make this like back to what it was basically. We can use the face tool, and it puts in the right direction. Then we'll use a corner round to smooth those. Okay, so that's fine. Okay, so now we don't have to worry about that melting through. Okay, so now the question is, do we have the ability... Oh, right, so now we can do a button head on this side, and then we've got plenty of room for the nut over here, because we don't have to really worry about it hitting anything, because there's no rivets on this side. So we'll do a button head on this side, and we'll put the nut over here, and then over here we'll flip it around, and we'll do... yeah, I guess this is the one that's more the concerned, going this way. So from here to there, oops, is more than 1/8 of an inch. Alright, it's going to be really close. Okay, so we need to put the bolts and the bearings in, I would say. So from here, actually let's measure it this way. So we can fit a 1.5 inch button head. I don't think we've got one of those in our library. I think it just was in the folder already. 1/4-20. Oh, I don't even have any 1/4-20 button head stuff. Alright, let's go get that model from Mcmaster-Carr. Come on. What's going on? What the heck? It's just... Is my internet, like... No? I mean, the stream's still up on my phone. What is going on? Why is this not... Oh, their website's working. Hex drive. Do I really have to, like, click through? Why won't it... The search is not working. That's so weird. Okay, quarter 20. Seems to be working normally now. Alright, 1.5 inch. Black oxide. That's a weird size. Those are really expensive. Those are almost $1 a piece. That's crazy. The zinc plated is considerably cheaper. We almost never buy zinc plated, but in this case you probably would. I mean, the strength is the same. So 25 for $11 or 10 for... No, why would you... Why is the zinc plated ones cheaper? That doesn't make any sense. Okay, well. Not to worry, we'll just do it and not question it. I think it's just a weird size. So BHCS, or no, we want to do screw 0.25-20 by 1.500. No, we don't add the zeros. Inches. ZP for zinc plated, because that's... And then, were we doing... Alright, we're doing the BHCS at the end. That stands for button head cap screw, in case you hadn't picked up on that. Okay, so now let's import it. I need to clean out some of these step files in here, because once you import them, you don't need the step file anymore. And step files are fairly large because they're ASCII files. They're not binary files, so all of the like part data is basically in text format, which means it's about 10 times larger than it would be, probably more than 10 times actually, considerably larger than it would be if it was a binary file. I don't need to do that. Steel. Alloy. Let's do a zinc color. And let's turn on that axis. Alright, I hate it. I hate it's going to be the only zinc plated screw in the entire assembly. But it's fine. Okay. Alright, so screw like that. And then rotate that, like that. That's how the screws are going to go. So, oh, really? I didn't realize the heads were that large. That's obnoxious. Okay, well, nothing we can do about it now. Let's see if we can get them to fit. Yeah, see, it interferes. Shoot. Okay, well, let me finish constraining these, and then we'll see what we can do about that problem. Yeah, that was the advantage to using button heads, is the head diameter is smaller. But what is the head diameter on this, by the way? Oh, okay. So it's only a 1/16 of an inch larger than the button head, but it's just enough. Okay, so there's another approach that we could take to this, I suppose, which honestly would make our lives a lot easier in several different ways. We could use a much smaller screw, like a number 8, even maybe a number 6 that goes through here, and then the head is not going to be as much of an issue anymore. And then we can use like a 1/4 inch sleeve just between the plates. So we make the hole smaller in here for the small screw, and then this 1/4 inch sleeve just goes right in between. That'd be lighter too, because the sleeve could be aluminum, and the 1/4 inch bolts are not necessary for strength. They're just needed for their diameter. Plus, it's not super great to put a bearing on threads like this. With these up here, it was kind of unavoidable, and the bearing's not completely on the threads. It's like halfway on the threads here, and it's completely on the shank here. Down here, it's just like there's no hiding it. They're just both of the bearings are completely on threads, so that's not super great because it doesn't really support the bearing. Plus, the actual outer diameter of a threaded part tends to be slightly smaller, so there'll be some slop too. Alright, so these are clearly not going to work because we absolutely cannot cut any more off of this, and we can't move this in. I suppose we could machine the head of the button head screw down, but that's too much. That's too jank even for me. There's Stellar's motto is sketchy at best, but that crosses a line somewhere. So, okay, let's stop talking about it and let's design the sleeve thing here. Okay, so what we need to do is make this like 0.177. Actually, wait a minute. What is the... I don't actually know what the diameter is off the top of my head. Oh, 0.164. Okay, well, that was easy. I did know that one. I thought that was a different size, but I guess it makes sense. All right, anyways, 0.164 plus 0.005. And we'll make that the same as that. Okay, so those are our holes. Okay, and then we need the sleeve, which is going to be very simple. 0.255, or no, 0.164 plus. And this should probably be 0.249. In reality, you would just buy 1/4 inch stock, drill a hole through the middle, and then sand the outside diameter down. It's a thinner wall than I was hoping for. And then 1 inch long is fine. I wonder if you can buy that part. Might be able to buy that part actually. Spacers. Number 8. OD, 1/4 inch. 1 inch long. 44 cents. You know what? What type of aluminum is it? Material can vary between 6061 and 2011. Alright, that's kind of unspecific, but we'll just call it 6061. Alright, so I need this part number, and then this is ID 166. Oh, it's a really close fit. Actually, that's even better. Alright, so it's literally a 2/1000th oversized for that screw, which is pretty crazy. That's a very close fit for a bolt. Okay, typically put spacers and standoffs in fasteners as well. So we'll do spacer. We'll do 832. It could be used for another size, but 832, 0.25, 0.25 OD. 1.0 long aluminum. And then the part number. Anything else that we need to specify? No, that should be good. Okay, save that. those in here. Okay. I'm going to use the insert constraint to put these in here. Where'd they go? On their way over here. Alright. We're slowly but surely getting there. This would probably go slightly faster if I wasn't recording, because I would be putting less thought into talking and more thought into actually modeling, but for the most part, doing stuff like this is just very time consuming. Okay, so we could use a 1.5 inch screw. I still think that a number 8 nut is still taller than 1/4 inch. I suppose we can look. Mm-hmm. 15/64. Actually, that is 1/4 inch. So yeah, they're just under 1/4 inch, not 1/8 inch. So yeah, that's what I thought. So the nut's still too big. We do need to find. Let's do button head. I don't know why the search wasn't working. Like, it was working fine now. All right, let's do 832. And let's look at sizes here. So 1 1/4 won't work. 1 3/8 would work. 1 1/2 would work. So 10 for, oh, they don't even have zinc plated that long. So 1 1/2 would work. So 1 3/8 is actually significantly cheaper. So we'll just do 1 3/8 because that's like the perfect size. Fully threaded. Save the step file. Oops, not done downloading yet. Alrighty, making progress here. Spending all our time importing components, which is how that usually goes. Screw 832 by 1.375 long. BHCS. And then I'm not going to, for black oxide, I typically don't put any kind of an abbreviation for the finish, because if I don't put an abbreviation, I just assume it's black oxide. Also, this detailed information is not super critical for what we're doing, because typically we don't actually use Inventor to generate a list like of part numbers that we need to order. We kind of just open up the CAD model and look at what fasteners are there, or just we write it down on a piece of paper as we're CADing it. Like, if we build this, we need this fastener. It's a very, very, I guess, what am I trying to say? I keep thinking unprofessional, but that's not what I'm trying to say. It's a very casual process. I can't think of the phrase I'm looking for right now. All right, steel alloy. Yep. And I usually use glossy black just because I hate all the other black textures. Even though black oxide screws are not glossy, I still use the glossy texture because the other ones don't show up right. Okay. Now we can constrain these all in and hope the heads are small enough where we're not worried about all the interferences, which I think they should be okay. If we absolutely needed to, we could probably go down to a 632 and still have enough strength. There's not really going to be that much load on these, and they're in shear, so they're fairly well supported. They're double shear on both sides. I mean, depending on what you're using this mechanism for, you could see some impact loads. gets close. Because, like, if this rolls by, like that is so close to that screw head. Yeah, that's not going to work. How much vertical space do we have? See, we just don't have that much vertical space either. So from this like little ring right here to there is the 1/10 of an inch. Wow. I don't have a good answer here. I don't think going down a size in the screw is really going to make enough of a difference that we're going to solve this problem. I suppose if we really wanted to, we could go to a flathead and countersink these holes. It's not a great option, but it's not impossible. I mean, it would definitely solve the problem. And we really only need it here and here. We don't really need it here. I kind of hate that, mixing the fasteners like that, but the flathead really takes some strength out of this. You know, we'll just buck up and do flatheads on both. Alright, now we need to go download another fastener. Alloy steel, flat, hex head, 8, nope. 832. Okay. Alright, 1 3/8 is twice the cost of 1 1/2, of course. About, yeah, they don't even have them. Zinc plated 1 1/2 are quite a bit cheaper though. Head height, 1/8 of an inch. So yeah, the problem that you have with these is when you're putting them in material that's this thin, you actually have to countersink this too. So you can't just countersink the plate, because the head actually goes down all the way through the plate. So you lose some locating ability in the plate when you use a flathead screw on something this thin. Which is why I really hate doing it. I just try to avoid flathead screws at all costs. We're just going to go ahead and do it because we're kind of stuck in this rut working on this stupid bearing assembly down here, and I kind of want to get off of this and go do something else, and then come back to this later and maybe remodel it if we think of something that's significantly better. So I'm just going to download this screw. We're going to drop it in there, see if it'll fit, which it should. Oh wait, I don't want the black oxide one. I want the zinc one. Like I said, we don't really order from the part numbers necessarily, but I like to have the part number, the correct part number in there just in case we do. Screw. .32 by 1.5. Actually, I don't need the LG. I don't know why I put the LG on that other one. Yeah, we don't usually put that. Okay, so FHCS for flathead cap screw, ZP for zinc plated, and then delete all this other junk. Okay. go. We've been at this an hour and a half already. Haven't gotten a whole lot done. I'd hope to get more done than this. But we're working through some tough issues here where this is all, I mean, this is just not an easy mechanism design. That's just really the truth of the matter. Just gonna shift select all those. I would say this is the hard part, but this is probably just one of the hard parts. This is just not an easy thing to design, and me not having done it before means I don't have any real tricks or anything that I'm used to using. Now, I'm not going to countersink these holes, because the way that you would actually manufacture this is you would have it laser cut like this, and then you would use a hand drill and countersink them yourself afterwards. And so for laser cutting, you don't want to model the countersunk hole, because then the laser cutter will try to cut. Well, here, I can just demonstrate. So if I put a sketch here and I project this geometry and then I put a hole, actually, yeah, no, I'm just gonna do it this way. Okay, and I put a hole here and I do like a clearance for a number 8, and then I put a countersink. So you see how, because the countersink goes all the way through, it basically makes the hole bigger. The laser cutter would cut this, not the inner one, because the inner one's just gone. So like there. So now on this side, the hole diameter is supposed to be 0.169. Over here, the hole diameter is 0.223. So undo all that. So that's why I'm not modeling the countersink. There's some other ways you could go about getting the countersink in there, but still having a model that has the right hole size in it, but just not worth the time it takes to do that type of a thing, and it makes it harder to change stuff later on down the road. So I'm just going to do this. There's just all kinds of interferences and weird, intersecting plane glitches and stuff for doing it, but this is the easy way to represent what we're trying to do here, and it looking good in the CAD is not really super necessary, because even if you were to render this, you wouldn't be able to see this bearing assembly in here. So laser cut the way it is, and then countersink it manually, and probably hit the standoff with the countersink too, because as you can see, wow, that is like, actually, I think probably what you would want to do is not countersink this plate all the way. So you'd actually want this screw to stick out a little bit, because the screw actually breaks all the way through. I think you'd want to pull this back, which you can do a decent amount. Once again, we're just doing sketchy stuff here. So you can come out almost a 16th. We'll come out 50 thousandths and see what that looks like, because we can adjust this. Oops, wrong direction. It should be negative. I'm just editing all of these constraints. So you can do something more like that, because that will clear this rivet by a decent amount, but it still leaves, and actually that way you only have to barely hit this standoff with the countersink, and actually the standoff might come with a small chamfer there just for the deburring operation when these are machined. So you might not even need to do anything to the standoff. There might be enough of a radius or a chamfer on that edge that you don't have to worry about it. Alright, so that's that. So we're clearing rivets now. It's an absolute train wreck, and I do not like it, but I don't want to work on it anymore. So we're going to go ahead and throw some bearings in there and call it good. In addition, because we shortened this flange, our bearings actually don't hit anymore. So like this bearing doesn't actually hit this flange anymore. So that's kind of an interesting side effect. So that actually means that we don't need to put just one bearing on this side. Because we were going to just put one bearing here, we could go ahead and still put two. So I think that's actually what I'm going to do. Alright. Bearings. That guy. 1, 2, 3, 4, 5, 6, 7, 8. And then what I'm going to do is use this guy. This is going to be kind of a pain. Look at that. Now this bearing will actually rub against this plate. I don't know if that's really avoidable, because in order to get a little spacer in here that only contacts the inner race of the bearing, you have to space it off quite a bit. And then you're going to start interfering here, because remember we have this notch here, so that this bearing can't interfere here. So I think the strategy for this needs to be, you have this little spacer in here, you make the spacer a little bit undersized so the bearing has some float left to right, so it's not necessarily always shoved against this plate, and then just hope it runs free enough that it's not an issue. Not a super great way to design it, but that's what I would do. I don't really think it would cause that much of an issue. But I suppose an alternative to that would be, if you wanted to, how do you, yes, bevel disc springs. So you can use one of these with a 164 ID, which is exactly the size, which is kind of unfortunate. So OD, thickness, height. So you can get one that's like, you can get 12 of them for $10. So they're actually meant for springs, but they're basically just conical washers, which actually I should just look and see if, because conical washers are also a thing. Oh, I'm thinking of a sealing washer, not because a conical washer is just a disc spring. I'm thinking of a sealing washer, not a. Yeah. Okay. So this is just the same thing as a conical washer. What I was thinking of, but okay. So so you could use this, and it's only 24,000. So these are really, really thin. I mean, there's other ones down here too that are a little thicker. Now, normally these are, like this takes 25 pounds of force to deflect. So, but you're not really interested in that because they are springs, like they do act like springs. And so in an application like this where you're not actually going to tighten the bolt down because you'll bend this flange, it'll basically just act like a spacer, but it's cone shape. So if you put the cone facing like this way, like so the cone is angled in, the peak of the cone will contact the inner race of the bearing, and then the outside part of the cone, like this part out here, will contact the aluminum. So that would be probably the right way to do it. And I suppose if we wanted to, we could put in an offset so there's enough room in there for something like that and see what that looks like. Put down here. 24,000. 24,000. See, we still got plenty of room here. So spacing them out that much. The problem is this is just too small of an area to 3D print anything. And using an actual flat washer is not going to work because the flat washer for a 1/4 inch diameter is like almost as big as this bearing is. So it comes way out here. It's 7/16, or wait, no. Actually, it might be bigger than the bearing. 1/4 inch flat washers are quite large, and you couldn't really get a small enough diameter one where it would only contact this inner race because the inner race is so small. So basically, The disc spring is the only way to accomplish that because it's a cone shape. And it just happens to work in this application because it's not really being compressed because you're not actually tightening the screw down, because the screw is really just a shaft. It's not really doing anything. Now, in actually this case, in this particular case, because there's a spacer in here, you could tighten the screw, but you're not tightening the plates down, right? So the plates aren't going to, everything on this shaft isn't going to be tight because the plates won't move because they're bottomed out against the spacer. So I don't know. It's like, I don't know. I'm kind of brain dead here, so forgive my rambling. Let's finish constraining these, and I'm going to put that 0.024 spacing in there. Disc springs are a little bit expensive, just because, I mean, they are springs. Like, they're not washers in the sense of like where normal flat washers are basically just stamped out on a blanking press, and then they're tumbled to deburr them, and then maybe plated. Oops. And so flat washers are like stupidly easy to produce. However, disc springs require that they be stamped and formed into the actual cone shape, and that cone shape is very, very critical because the cone angle, outside diameter, inside diameter have to be pretty precise, and then also the wall thickness of the cone has to be really precise because all of that affects the spring rate. And typically when you're using disc springs, you're using disc springs in an application where you want precise control over the load the spring provides, which is why... Oh, did I close that? I can't believe I closed that window. Why did I do that? All right. So you can stack them like this, and this changes the spring rate, changes the load, so you have very, very precise control over the spring forces involved. And so it's very critical that the spring is dimensionally correct, and then obviously it has to be heat treated as well. So all of that stuff makes them significantly more expensive than just flat washers to produce, even though they are geometrically nearly the same thing. And made out of the same materials a lot of times. But the dimensional precision and the heat treatment really drive up the cost. I'm not actually 100% sure. I'm not super familiar with the heat treating process that goes into making those. I suppose it's possible that they're heat treated before they're stamped, but I wouldn't think that would be likely. I suppose it's possible, but not necessarily likely. Okay, well, this is horrible. Not super happy with how that turned out, but it does accomplish what we needed to accomplish. There'd be nuts on these, but I'm not going to put them on right now. We took nearly 2 hours to figure that out, and this bolt. So in 2 hours, we've gotten, a few bolts and a couple of plates done. But we solved some really difficult problems. So with our remaining time, I think what we're going to do is plug in my phone because it's almost dead. Like I mentioned last week, I have this, I'm at my desk and I've got the phone on the desk in front of me with the stream pulled up so I can see the chat because I only have one monitor on my computer, so I can't pull up the chat or something beside without it showing up in the stream window, which would be really obnoxious for you guys. So yeah, I've got the stream up, and obviously my phone screen is on, so it runs out of battery pretty quickly. Alright, let's turn on visibility for just that guy, because now what we need to do is put the other belt pulley down here and put the belt in. So in order to do that, we need to decide on a belt center to center distance. So let's open up get this belt calculator up here. This is sdpsi.com. Design tools, center distance designer. If you've never used this before, it's really, really nice. So we pick our 5mm HTD. We probably could get away with a different belt pitch than this. It's just because I'm planning on 3D printing these, or hypothetically I would 3D print these if I were designing this for something that we'd actually build. Then the bigger the teeth in the belt, the better. We could use a GT2 3mm pitch, which would be probably a little bit more appropriate, just because the actual torque transferring ability of the belt is not really that critical, because it's all of the forces are directly translated to the belt itself, because we're going to like clamp the belt to the tube, and so then these are just idlers. They don't transfer any torque, so the size of the teeth is not really an issue, and a GT2 belt like can physically take the tension, I'm sure. And this is not really meant for like climbing or something, so I don't think you'd be snapping belts. But I don't really know. That's mostly just a hunch. So, okay, 18 and 18, and then we need to figure out like what we need to get close to. We pretty much want it 35 inches. So we like 34, maybe. Oh, it's in millimeters, right? I should have looked at the metric one, not the English. It's like 800 and... yeah, so... it's like 860... 362 teeth. Alright, so we don't want one with an asterisk, because those are belts that they don't stock. We want ones that are not starred. So we've got 360, we can go up to 369. So this gets us 33.6614 inches. If we go up to 369 teeth, that gets us about 34 and a half. Alright, let's open up this part. Okay, so we basically need to mirror this down at the bottom, but we can't actually mirror it because it's not going to be centered vertically on the part. It's going to be some weird distance away because of the center to center distance. Okay, so I need to basically model this the same way that I did here. So center point rectangle, 1.75, 0.7 inches wide, 1 1/8 from that side. Okay, so here's what we're going to do. Project that line and that line, and make a line across here. Okay, and then 1.125 from there, because it's not actually centered in this part, because there's that 1/8 of an inch. I thought I turned that message off. Hate the save reminders. It's like I know I'm saving my stuff usually. Okay, so that's the center line of the belt. So we're going to dimension from there to here, and we're going to do, let's see how close to the edge this gets us, because ideally we go as long as possible. So 877.5 millimeters. And then we're going to add 10 thousandths. Okay, so that's too close to the edge. So we've got to go down to the 360 tooth. And let's actually see, do they even carry this in 9mm wide? 9mm wide single-sided neoprene. 0 in stock. Price is not terrible for such a weird size belt. Let's see if V-Belt Guys has it. Okay, so it's 360 teeth, so that's a pitch length of 1800 millimeters. So it's going to be 1800-5M-9, because 9 is the width. Actually, I don't know if Google searching it actually works. Let's see. Look at that. Look at them go. They do have it, and it's like a quarter of the cost. So it's $650. Yeah, that's awesome. Now it's like quite a bit. Oh, that's a 99. Yeah, so like there you go. So it's really these guys. I've never actually ordered anything from these guys because I first heard about this website from Spectrum's build blog. So I first heard about these guys this year, and it was after we had already ordered all of our belts for our robot. And so I intend to use these guys next year because they are significantly cheaper than Vex, West Coast Products. They're significantly cheaper than SDPSI is. And they have a lot larger of a selection too, so it's kind of just a win-win. I'm not sure what's going on here. I don't know if this is like retail price and this is the price that they offer, or if this is like a temporary sale. This has always been this way. Like most of their belts show this, and it hasn't changed since I've been using their website, but that's only been a few months, so maybe it's just a long running sale. I don't know. But either way, they're very cheap. Inexpensive, not cheap. Okay. What was I going to do? 855 millimeters. I need to actually put this in and make sure this works. 855. That's considerably better. Okay. I would have liked to get a little bit farther down, and I suppose we could, I don't know, let's look at like 364. What would that be? I doubt they're going to have it because it's custom for SDPSI, but V-Belt Guys has a larger selection. So maybe we'll do 364, which is 1820. 20-5M-9. Yeah. Well, let's just start doing, I'll start going up. 1805. 1810. I don't think they have 15 or no. Yeah, they just don't have it. Okay, so 1800-5M-9 is the one that we're on. 5M. Oops, I don't know how I got a 3 in there. I think I hit it with my thumb. Okay, so that's basically our only option then. So yeah, that's okay. That's not a problem. Okay, so we'll cut that out. And how did we locate this? From the bottom. So this is D105. So now we're going to do that. So it's going to be D105 divided by 2. And then we can attach our center point, which would be 0.255, and I think it was 1.52. I think it was Okay. Alright, so then we'll cut that. And then we need to add this whole pattern, which is 0.625 and 3/16 away from the edge. And then it's done using the same trick, coming up, measuring up from the bottom. Okay, so it's 9 o'clock now. I'm going to go ahead and finish up this this here. I probably won't do the assembly work because I'm getting pretty tired, but I'm going to go ahead and get this whole pattern in here and just take a look at it. Alright, so that's 0.625, and then this is 0.1875, and then a center point at each corner. Well, for the 3 of you who are still watching, thank you for sticking it out. You guys sat through a lot of boring stuff, that's for sure. And I know one of those people is my phone, so there's only actually 2 of you watching. But I don't know who you are, but thank you for sticking around. Hopefully the next stream, I do intend to keep doing these. I don't know if I'll be able to do them more than once a week, so most likely if I don't get to it this weekend, the next one will be next Tuesday, just because that's really the only evening that I'm not doing something else. But I do intend to keep doing this and hopefully finish this project, and hopefully the next ones are quite a bit more interesting. Okay, so now what we're going to do, let's just take a look here and see if there's going to be any issues with interferences here, because the answer is very likely yes, although it doesn't look too bad. I think I'm just going to go ahead and assemble this. I didn't really want to spend the time, but I kind of want to know, so curiosity is getting the best of me. Okay, so T6 goes on the inside. Season, telescoping arm, T6. So T6 goes, and I am on the right side, right? Yeah. So T6 goes on the inside, and then T7 will go on the outside. So we go from there to there, and then the bottom one as well. All right. Oops. All right, and then T7. Can do it this way. I'm actually going to flip it left and right. Not particularly important, but I just wanted to maintain the same order of placement of the parts. Not really critical at all. It's mostly just a way that I keep them organized, the assemblies, that is. Alright, so then this guy, how is this constrained? Yeah. Okay, so now we need to put the dowel in. That one, 0.5, like so. Constrain the axis. And then this face was supposed to be 0.01. Should be the same on the other side. Close enough. Okay, so now we can do the pulley assembly, which has already got the bearings and stuff in it. Oops. So we can constrain the center line there, and then the inner race of the bearing should be 0.035. Okay. Now I'm going to hide this so I can look at the inner action. Oh, that looks pretty good. Is there enough room for the nut here? There's most likely enough room there, yeah. So the screw itself gets really close to this 3D printed part, even might even touch it a little bit. There's a little bit of a gap there. But in reality, the nuts was the main concern. This end of this screw could even be cut if it had to be, because the screw is too long. Or you could just hit the edge of this 3D printed part with a file to solve that problem. I don't think the rotation on something that's this long is a pain. Do these touch? These do not touch. Oh, you know what is a problem though? The spacing between this and this, that was intended to work with the belt being directly on this piece, but this aluminum is in the way. Alright, well I think that's a problem for next time. I think I don't have enough brain capacity left to solve that. We could potentially space this out, or even potentially use this as the clamping device for the belt. That might be a creative way to solve that problem, because we do need to clamp the belt to this tube somehow. And so if we just somehow found a way to trap it underneath that plate, that might be something we could do. There's also other options where we can put some bent pieces or something and do something that way that mount to the sides just for one side. It wouldn't work for these other three, but we can do it for one side. That's probably the right way to do it. But yeah, we'll figure that out next time. So let's turn the visibility back on. So not a lot of visual changes, but made a decent amount of technical progress. All right, well, thank you for watching. This will be continued in the future. I'll post links and stuff in the same Chief Delphi thread, as well as on Facebook and Twitter. So thank you for watching, and I will see you guys next time.